whenever.
Okay, ladies and gentlemen, you are going to be filling out a handout that looks like this, except yours is not going to have any of the things filled in. You have to fill them in as I go. So forces are pushes and pulls. And a force is anything that is going to be a push or a pull. And forces have direction. It matters what direction you're pushing or pulling, and forces have size. It matters how hard you're pushing or pulling. And we use vectors or arrows to represent a force. So the length of the arrow is the size, and the arrowhead shows the direction. Now, just like when we had motion, we can have a positive direction where we're moving from left to right, or we can have a negative direction where we're going from right to left. So draw a force vector in the positive direction. You're going to draw one from left to right. Now, very rarely is there just one force acting on an object. Forces occur in pairs often on an object. And when we have forces in a pair that look like this, these are a balanced force pair. So they are a pair that are equal, they're the same length, but they're in opposite direction. So this here would be a balanced force pair. Draw that on your paper. Now when we combine balanced forces, we have a positive force and we have a negative force. And so we say that this has a net force of 0, and newtons is our label. Because if we have this arrow, if we assign that to be a positive 5 newtons, and we assign this to be a negative 5 newtons, when we combine those, we get an answer of 0. So balanced forces have a net force of 0. And the net force is simply the total of all of the forces acting on the object. You add them up. You add them up being positive or negative. So if we have forces that are acting against each other, then we subtract. But if we have forces that are working together, we're going to add those together. It's like two people pushing, helping each other out, where this would be two people pushing against each other, trying to cancel each other out. Forces acting at angles are not pairs. Pairs are either in the same direction or pairs are in the opposite direction. So we're never going to have forces acting at angles because they are not pairs. So if I have an object and I have 5 newtons on this side and I have 10 newtons on this side, write the net force in the box. And then for the second example, what is the net force? I have my 5 newtons and I have my 10 newtons, and now 10 newtons is in the opposite direction. Write the net force in the box. Now, those were balanced forces, but we can also have unbalanced forces. So let's talk about unbalanced forces. Unbalanced forces are forces that are not equal and opposite, and the net force of an unbalanced pair is not 0. So an unbalanced force, so if we have a force pair here, let's go back to the 5 and 10 newtons, that they're opposite, but they are not equal. And whenever we have an unbalanced force pair, whenever we have forces that are not equal but opposite, they are always going to change the motion. So unbalanced forces will always change the motion. So if I have this object and I've got it moving to the right, this force, just like in the bowling ball and the push-o-meter, when I worked against my motion, it caused it to slow down. If I have, let's switch this over, let's say this is 20 newtons, there's my object, and this is 4 newtons. My net force would be 16 newtons. right. Up here my net force was 5 newtons to the left. Oops. So here, if this is my object moving to the right, now I've got my net force is in the same direction, so this object is going to speed up. So unbalanced forces have a net force that is not 0. Unbalanced forces will always change the motion. Unbalanced forces will always cause the object to speed up, slow down, or change direction. Remember when we had the bowling ball in the pusher meter and we pushed it to the side? Our motion was constant, then it changed direction. That is a change in motion. So at the bottom of the first page, please draw a motion map for the motion of an object with the following force acting on it. Before the force acted, the object was moving to the right. So this is your force, and then your motion map. This is your motion map you're working off of. Before the force, we're acting to the right. So finish that motion map for me, please. The second motion map that you're going to draw on top of the second page, you have this force acting on it. And again, our object is moving to the right before the force acted. And then the third one you're doing, we have forces like this. Now in this case, we didn't talk about this. In this case, the force is not unbalanced, but these are balanced forces. So if the object is moving to the right and we have balanced forces, what we're going to see is a constant motion, because we don't have one force overpowering the other force. They are the same size, they're balanced, they're going to cancel each other out. The second page now, 4 kinds of forces. Whenever we draw force diagrams, we need to draw and label all of the forces acting. The first one, number 1, we have the force of gravity caused by the pull of the earth. And gravity is always going to pull straight down. So that would be a gravity vector, and we would label it force of gravity, F subscript G. The second one is the normal force. Let's label number 1, gravity, normal force. Normal force is an upward force on any surface the object is resting on. So if the object is on a surface and not moving up or down, then we've got gravity pulling down on it, because gravity is always there. But now we have this normal force that is balanced gravity, F sub n there. So if the object is on a surface and not moving up or down, the normal force is balanced with the gravity. So gravity and friction there, or normal force and gravity moved. Third one is friction. Now friction is always acting on a moving object. So only when the object is in motion do we have friction. And friction is always going to be opposite our motion. So F sub F there. So direction is always going to be opposite. So if an object is moving to the right, friction is acting to the left. So draw in the force vector for friction causing the motion here. So our motion is slowing down. We're moving to the right, slowing down. So if we're moving to the right, slowing down, then we have to have a force opposing that motion. We have to have a force working against it, and that would be our force of friction. If an object is moving to the left, friction is acting to the right. So draw the vector for friction causing the motion. I'm sorry, the motion is at the top of the next page unless I fixed it. But the object is moving to the right and slowing down. So if an object is moving up, friction is down. If an object is moving down, friction is up. So now on the side of the page you have a motion map where it is going up and slowing down. So draw the force vector and label it for friction. And then any push or pull that is applied by us is the applied force. So number 4 is the applied force. This is going to be any other force that's not gravity, normal, or friction. So an applied force, any push or pull on an object is the applied force. Any applied force can act in any direction and can balance or unbalance any force. So in the next object there, your last object, you are going to show gravity. You're going to label it Fg. You're going to show normal, Fn. You're going to show friction, Ff. And you're going to show an applied force. And this object that you're putting these forces on is moving to the right at a constant speed. So this is your motion map, and you're going to draw the force diagram showing all 4 forces across it. Then at the bottom of the last page there, you have balanced or unbalanced. Just write a U or a V in those situations showing whether the forces are balanced or unbalanced. Bring this tomorrow to class completed. Thank you. Have a good night.